Welcome back to AI.Code.Cast, where we love to kind of break down those coding challenges that sometimes make you scratch your head and go, huh, wait, what was that? And, well, today we're going to dive deep into one that's all about sums and subarrays. It's called the continuous Subarray sum problem. I'm really excited to have an expert with me here today to help us kind of unpack all of this. So are you ready to get our hands a little dirty with some code?
Absolutely. I think this is a classic problem that really highlights, the difference between just like a raw brute force approach and something a bit more elegant. So let's start by just painting a picture of what the challenge actually is.
Okay.
So imagine we have an array, which is basically just like a list of integers. And we also have another integer, which we're going to call k.
Okay, so I'm picturing like a list of numbers. What is that K all about?
So that k is kind of like our target, if you will. So the goal is to figure out if there's a continuous stretch of numbers within that array, at least 2 numbers long. That adds up to a multiple of k.
So we're trying to find a slice of that array where the sum is, like perfectly divisible by K.
You got it. Now, the first instinct for many, especially when they're starting out with algorithms, is to just check every single possible subarray. Let's unpack that for just a sec.
That sounds like the brute force method that you mentioned earlier.
Exactly. It's like trying every single key on a giant key ring until you find the one that unlocks the door. It'll work eventually.
Yep.
But it could take a really long time.
Yeah, I can imagine. So walk me through what that would actually look like in terms of the code itself.
Well, you could use nested loops. So one loop would mark the beginning of your subarray, and the inner loop would basically sweep through all the possible ending points from that starting position.
Okay.
And for each subarray that you form, you'd sum up the numbers and then check if that sum is divisible by k.
So it's like systematically scanning through all those different combinations.
Right.
And I could see how that could get really computationally expensive,
Yeah.
especially if we're talking about a massive array.
Exactly. So if our array has n elements, the outer loop would run times. And for each of those, the inner loop could potentially also run up to n times, which means our time complexity just balloons to big O of n squared.
O of n squared. So that means like that the time it takes grows like way faster as our array gets bigger.
Yeah.
Not very efficient. So there's got to be a smarter way, right?
There is.
There's got to be some secret weapon in our coding arsenal.
There is. And that's where things get really interesting.
Okay.
So instead of like repeatedly calculating the sum of each subarray, we can use a clever trick called prefix sums to kind of pre-compute the sums up to each index. And then with the help of a hash map, we can unlock a much more efficient solution.
Okay, I'm intrigued. Prefix sums and hash map. It sounds like we're about to level up our coding skills here.
Let's break those down one by one. Prefix sums first. What are we talking about here?
Yeah.
Imagine you're walking through our array and like adding up the numbers as you go. The prefix sum at any point is simply the total of all the numbers you've seen so far.
So if our array is, say, 2, 7, 5, the prefix sums would be 2, 9, 14, right? Because 2 is the sum up to the first element, then 2 plus 7 gives us 9, and so on.
That's it. You got the hang of prefix sums. Now, instead of storing all of these prefix sums, which, could take up a lot of memory, we're going to use a little modular arithmetic magic.
Modular arithmetic. You're not talking about those old school clocks with the hands, are you?
Not quite, but you're on the right track with cycles and remainders. So instead of storing the prefix sums themselves, we're going to focus on what's left over after we divide them by k.
So we're talking about remainders. Like if we divide 10 by 3, the remainder is 1. But how do remainders help us find a subarray that sums to a multiple of k?
Here's where it gets really cool. If 2 prefix sums have the same remainder when divided by k, it means the subarray between those 2 points must have a sum that's perfectly divisible by k.
Wait a minute. I think I see the connection. If the remainders are the same, it's like those 2 prefix sums are lined up on some kind of number wheel.
That's a great way to visualize it. Now, to keep track of these remainders and their positions in our array, we introduce our secret weapon, the hash map.
Yes, the hash map. It's like a super organized filing cabinet where we can quickly find information based on a specific key.
Exactly. In our case, the key is going to be the remainder, and the value is going to be the index where we first encountered that remainder in our array.
So as we walk through the array, calculating the prefix sum and its remainder, at each step, we check our hash map. What are we looking for?
We want to see if we've encountered this remainder before. If we have, and the distance between the current index I and the index stored in the hash map for this remainder is at least 2 bingos, we found our continuous subarray.
We found a continuous subarray that meets our criteria, so we return true.
Exactly. But what if the remainder isn't in our hash map yet?
Then we add it to the map, along with its corresponding index I. This way, we're always keeping track of the first time we encounter a specific remainder.
Makes sense. And if we reach the end of our loop without finding a suitable subarray, we know no such subarray exists. In that case, we return false.
This pseudocode is really helpful. It's like a blueprint for success. Our listeners can take this and implement the actual code in their favorite programming language.
You got it. But there's one more optimization we can sprinkle in. Remember that pigeonhole principle we talked about earlier?
Ah, yes. The one about pigeons and pigeonholes. How does that apply here again?
Well, our remainders, when we divide the prefix sums by k, those are our pigeons. There are only k possible remainders from 0 to k minus 1, which act as our pigeonholes.
So if our array has more than k elements, we're guaranteed to have at least 2 prefix sums with the same remainder. That's the pigeonhole principle in action.
Exactly. So before we even start calculating prefix sums, we can add a simple check. If the length of our array is greater than k, we can immediately return true.
That's such a neat trick. We can save a lot of computation time, especially for very large arrays.
Yeah.
I'm always amazed by how a little mathematical insight can lead to such elegant optimizations.
It's a beautiful thing. And, exploring these optimizations and variations is what makes algorithm design so engaging. For instance, what if we wanted to find not just any continuous subarray that sums to a multiple of k, but the longest one possible?
That's a great question to ponder. It seems like we need to tweak our approach a bit.
Yeah.
Maybe keep track of the lengths of the subarrays along with their remainders.
Exactly. It's like adding another layer of challenge to our puzzle. But remember, the journey of solving these algorithmic riddles is just as rewarding as the destination.
Well said. So to all our AI.Code.Cast listeners out there, we encourage you to explore these variations, experiment with different approaches, and keep pushing the boundaries of your coding skills.
Absolutely. After all, that's what makes the world of algorithms so fascinating. There's always a new challenge waiting to be tackled and an elegant solution waiting to be discovered.
All right, so let's get this pseudo code kind of cooking here. First things first, we need a place to store our remainders and their indices, right?
Right.
So we'll create an empty hash map. Let's just call it remainder map for now.
Perfect. Now we need a variable to keep track of our running prefix sum as we move through the array. We'll call that current sum and initialize it to 0.
Okay, so current sum, that's going to store the sum of all the elements we've encountered so far.
Yeah.
What's next?
Now we're ready to loop through our input array, which we'll call nums. For each element at index I in our array, we'll update current sum by adding the current element to it.
Got it. So current sum is continuously growing as we traverse the array.
Exactly. Then we calculate the remainder of current sum when divided by k. We can store this remainder in a variable called remainder.
Okay. All right, so remainder, that's going to hold the key to our hash map.
Yeah.
Now we need to check if we've seen this remainder before, right?
Right. If remainder already exists as a key in our remainder map, and the difference between the current index I and the index stored in remainder map for this remainder is at least 2, we've struck gold.
We found our continuous subarray.
Yeah.
We found one that meets our criteria.
Yeah.
So we return true.
Exactly. But what if the remainder isn't in our hash map yet?
Then we add it to the map, along with its corresponding index I. That way we're always keeping track of the first time we encounter a specific remainder.
Makes sense. And if we reach the end of our loop without finding a suitable subarray, we know no such subarray exists. In that case, we return false.
This pseudocode is so helpful. It's like giving our listeners a blueprint for success.
Yeah.
They can take this and implement the actual code in, whatever their favorite programming language is.
I think it'll be really helpful for them. And on that note, I think we've reached the end of our deep dive into the continuous subarray sum problem.
Yeah.
We really hope you've enjoyed this journey through prefix sums and hash maps and all these clever little optimizations.
It's been a lot of fun.
Oh.
And until next time, happy coding, everyone.